Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the blind Leetcode 75 problem list. Today I will be solving problem 230, which is called kth smallest element in a binary search tree. So let's get to read the problem statement. Given the root of a binary search tree and an integer k, return the kth smallest value, one indexed, of all the values of the nodes in the tree. So example 1 right here, we have this tree, and since k is equal to 1, we return the smallest element, which in this case is a 1. In example 2 right here, k is equal to 3, so we return the third smallest element, which in this case is a 3. And some of the constraints is that the number of nodes is n, and k is guaranteed to be less than or equal to n. Okay, great. So if you want to give this problem a try by yourself, now would be the time to pause the video and yeah, because I'll explain the solution right now. So the naive solution, right, to this would be to simply traverse the entire tree. And if we traverse the entire tree and store all the elements in an in-order traversal in an array, it'll give us an array in which the orders are listed from the smallest to the biggest, because again, we're performing an in-order traversal, and then simply returning the element at index k minus 1 would suffice. And for sure, that works, but that would require us to traverse the entire tree every single time we do this problem. And as we will see in a bit, that's not really necessary because we can use the properties of a binary search tree to our advantage. So what do we know about binary search trees? Well, we know that given any node, any numbers to the left of it, so the left subtree of that node, will be composed of numbers that are smaller than that of this node right here, the node that we're currently at. And any number to the right of it, so the right subtree of that node, will be composed of numbers that are bigger than the number of the current node. So how can we use this to our advantage? Well, like I mentioned before, right, we can perform an in-order traversal. Whenever we perform an in-order traversal, we first process the left subtree, then the current element, and then the right subtree, which means that we're always going to be processing the tree from the smallest numbers up all the way to the biggest. And how does that help us? Well, the main idea here, right, is to perform an in-order traversal, and instead of traversing the entire tree, whenever we just traverse k elements, then at that point we know that we've reached the kth smallest element, because again, we're traversing from smaller to bigger. So for example, let's go through example 2. If we perform an in-order traversal of this tree, right, we will do 1, 2, 3, 4, 5, and 6. And the actual, if we were doing this recursively, right, we would start at node 5, then we process the left subtree of node 5. So now we are at node 3. Here in node 3, we process the left subtree of node 3, so we are at node 2. Similarly, we process the left subtree of 1, of 2, sorry, and then we go to 1. And then for 1, we process the left subtree of 1, which is in this case a null pointer. Then we process a 1. Then we process the right subtree of 1, which is null, and then we pop back up. Here we process the 2, and then we go to the right children, which it has none of them. So we've processed 1 and 2. Then we go back to the 3, and, in 3, we process the current node, and then we would process the right subtree. So we process 4, then we process, after processing the left subtree, which is none, and then the right subtree, and so on. And then we process 5, and then we process the right subtree of 6. Now, as you can see, right, we're going from smaller to bigger, and that's why that traversal in this case is called in order, because it goes from smaller to bigger. The idea here is to simply stop the traversal whenever we have processed k elements. So when we're doing the in order traversal, right, we first process this element right here. And in order to keep track of how many elements we process, we can simply use this variable that's given to us right here, k, which is the kth smallest element, right? So if we want the second element, the second smallest element, then we know that whenever we have processed the second node, right, that means that that's the node that we want to return. So what happens then? We will simply, whenever we process a node, right, we will just decrease this number by 1. And whenever this number is equal to 0, then we know that that's the kth node that we want to process. So let's start with the example, right? In the beginning, k is equal to 3. And during the in-order traversal, we go all the way to node 1. At this point, what we do is we decrease k by 1. So now k is equal to 2 because we have processed one node. After that, we are k is equal to 2. And we find ourselves in node 2. And what do we do there? Well, again, we process the current node. So k is equal to 1 now because we decrease k by 1. And then we find ourselves in node 3. So k is equal to 1 here, and then we find ourselves in node equal to 3. And now what do? Well, we decrease k by 0. And since k now here is equal to 0, then we know that 3 is the kth element, the kth smallest element, in this case, the third smallest element. And at that point, we simply return this. And actually, it says that the return time is an int, so I'm guessing that we just have to return the value of this. So we would return 3, not node 3. But yeah, so that'll be the main idea behind this. And because the code comes out really clean whenever we do it iteratively, I'm going to implement this solution iteratively. But if you want to challenge yourself, make sure that, feel free to try to do it recursively. I've also implemented it recursively before, and what I did is I used some tuples to return the method, so maybe that can help you a bit. But let's get to code it, right? So first of all, right, we need some sort of data structure that will imitate the behavior of recursion. We know that recursion works with like different calls and keeps track of what level you're on, and that's similar to a stack. So obviously the data structure that we will need to emulate the recursive behavior will be a stack, which in this case in Python can be used with a list, because in a list you can append elements all the way to the end of the list and all at one time, like you would in a regular stack, and then pop the last element that was inserted, so the element on the right, in all at one time. So I'm gonna comment this. There you go. And right, what do we do now? Well, we need a pointer, right, to the current root. That's what we will use to traverse the tree. So current is equal to root. And now what we're going to do is, since k, it mentions here that k is guaranteed to be less than or equal to n, right? And that means that k, well, there will always be an element that we're going to return. So what I'm going to do here is I'm just simply going to write a while loop that is always true, and we will break it whenever we find the element that we want to return. And this will never run forever because the element is guaranteed to exist because k is less than or equal to n. So here, what do we do? So usually, right, when we're doing an in-order traversal recursively, it will look like this, the code. It will be like in order, root.left, process current node, and then in order, root.right. So how do we emulate this behavior right here? How do we go all the way to the left all the time? Well, the idea is that we simply just check what the current root is, right? So while the current root is not equal to none, so, while it exists, then what we will do is we'll append the current element to the stack. So stack.append current, and then we'll set current equal to its left child. And this will just make sure that we're always going to the left. And this part right here, recursively, is iteratively, is equivalent to this part right here, recursively. Now, what do we do? Well, we want to process the current node. But at this point, right, this loop will break whenever current is equal to none. So how do we make it not none? Well, we have been appending elements to the stack, right? So it follows that the last element that we appended is the number that we want. So current is equal to stack.pop. And that will be now the current node that we want to process. And how do we process it? Well, like I said before, the way that we process the nodes is by simply decreasing k by 1. So k is equal to k minus 1. And after that, we simply have to check whether k is equal to 0. Because at the point that k is equal to 0, then we have found our kth smallest element. So if k is equal to 0, then we return current. Actually, return type here is int, so it should be current.value. And after that, we have done this part and this part right here. So what do we do now? Well, we simply go to the right of the tree. And how do we do that? Well, pretty easy. Current is equal to current.right. And remember that here, right, we don't do a loop like we would do in here, because if we did this loop, then what would happen is that we will go all the way to the left as we can. We process a node, and then we will go all the right to as far to the right as we can. And we don't want to do that. We just want to go one element to the right, and whenever we're on that element on the right, then we want to process its left subtree first, and then that element, and then the elements to the right. And this code right here should work. I'm going to comment this because with that comment right there, it will not work. But yes. There you go. And I've tested this code before, so eventually beats, yeah, there you go. Faster than 97% of submissions. So yeah, this will be the solution to this problem. And now let's discuss the runtime complexity and the space-time complexity of this algorithm. So first of all, right, let's think about how many elements we are going to be traversing at any time. Well, whenever we go over all these elements, we are going to just, traverse, but at the same time, we're not going to be traversing only k elements, because in the beginning, right, if you see here, we start at the 5, right? We go 3, 2, 1, but we have traversed 5. So definitely our runtime is going to be bigger than k is equal to 3. Now, the idea here is let's think about the worst case. So what is the worst case scenario? Well, the worst case scenario here will be a tree in which the root is the smallest element and we just go all the way to the right. So imagine that, for example, right, in this tree, the node is just a 1. So it will look something like this. So we go 1, 2, 3, 4, 5, 6. So that's what the worst case scenario for our tree would look like. So in that case, right, if we want to find like the kth smallest element, like k is equal to 3, we're first going to process every single node. We're going to go through every single node on the tree. So that is already big O of n. And at one point, we're going to go back, and then we're going to stop at the kth element, which means that in total, we are going to be processing n plus k elements. So that will be the runtime of this algorithm, big O of n plus k. And in the base case scenario, right, if k is equal to 1, and like all the nodes are, so imagine that now the tree is reversed. So it looks like this. Okay, that's a little bit bad, but I think you might get the idea here. 3, 2, and 1. In this case, right, k is equal to 1, so we go all the way to the left, so we process n nodes, and then we stop here at the 1. So that'll be the worst case scenario. That'll be one of the base case scenarios. But actually, now that I think about it, never mind. I'm kind of lying here. I think that a better scenario would be this one right here. So suppose that we do a 1. So let's do a 2, 1, and then we do. Well, actually, ignore what I said. So the best case scenario, right? Okay. So right here, sorry, this might be a little bit confusing. I'm gonna go back to this example right here. So in this example right here, right, we simply return, we go all the way to the left, and the base case scenario is just this, right? We just, return that, and at that point, we've simply processed one element because we go all the way to the left of this node right here, which it has no children, And then after that, we just return this. So this is the best case scenario. Sorry, not the worst case scenario. The worst case scenario is the one that I said after. So I got the mixed, excuse me, for that. And that will be, imagine, right, that k is, so we have 6 elements, so k is equal to 6, 2, and 1. So here in the worst case scenario, right, we will just be going all the way down, and then just to process like all the left elements, and then we just go back up. So we will process n elements plus k. So if k is equal to 3, right, in this case, then we process all the elements here, and then we go all the way back. And whenever we're doing runtime complexity, we always look at the upper bound, so the worst case scenario. So that's why the runtime complexity of this problem is big O of n plus k. And what is the space-time complexity of this problem? Well, once again, right, in the worst case scenario, we are going to be storing the entire tree, which would be right here. So imagine that, like, we want to process any element and the tree is skewed this way. So in this case, we'll be storing the entire tree. Excuse me. We will be storing the entire tree on the stack. And at that point, we've stored every single node. So the space-time complexity will be big O of n. And that'll be it. So yeah, I hope you found this video helpful. Make sure to drop a like and see you on the next one. Bye-bye.